Alright, let's go ahead and move on over to chapter 10.4. In 10.4, we're going to start talking about population proportions now. Both calculating out a confidence interval for population proportions, the difference between population proportions. So both calculating out a confidence interval for the difference between population proportions and testing hypotheses based on the difference between population proportions. So let's check out an example here, 10.4.52, which is number 3 from your 14th homework assignment. This is going to be calculating out a confidence interval for the difference between two population proportions. So let me start off with reading the problem statement here. Considering the following sample information randomly selected from two populations. Sample size 1 was 250. And then x1 is 50. So once again, what that means is, of those 250 people sampled for sample number 1, 50 of those displayed the attribute of interest. Sample size number 2 is 50, and then of those 50, out of sample number 2, 25 displayed the characteristic of interest. Now, we're asked to do two different things. Determine if the sample sizes are large enough so that the sampling distribution for the difference between sample proportions is approximately normally distributed. So once again, to check that, all we have to do is make sure that the sample size multiplied by the sample proportion is greater than or equal to 5, and also that the sample size multiplied by 1 minus the sample proportion is also greater than or equal to 5. Now, since we're talking about two different samples, we're talking about the difference between sample proportions, basically we need to check to make sure the sample sizes were big enough on both the samples. So we're going to run through this twice, basically. Alright, so for sample size number 1, of course, N1 was 250, so we would have 250 multiplied by, now, sample proportion number 1. We're not given sample proportion number 1. We calculate it out. Sample proportion number 1, so p hat number 1, is of course the number of elements that display the attribute of interest divided by the total number surveyed, so 50 over 250. Then while I'm up here, I'll figure out sample proportion number 2, which would of course be p hat 2, and that's going to be 25 over 50. Alright, so now we're just going to go plug those values in. So sample proportion 1 was 50 over 250. And you calculate that out, and I got 50. Obviously greater than 5, we're good there. Now same thing, N1 is still 250. Now that's multiplied by 1 minus 50 over 250. And that's going to come out to be 200. Of course, greater than 5 again, so we're good there. So we know sample size number 1 is large enough to be approximately normally distributed. Now we got to check for sample size number 2. N2 is of course 50. And we got a sample proportion number 2 of 25 over 50. So of course that's just equal to 25. Or no, sorry, 50. Or no, 25. Sorry, I wrote it down wrong on my paper. Then same thing. N2 is still 50. Now multiplied by 1 minus our sample proportion. And that's equal to 25 as well. So all those values are greater than 5, so both sample 1 and sample 2 sizes were large enough that we can assume they're normally distributed, or approximately normally distributed. Now, for the formula to calculate an interval for the difference between population proportions, it's your point estimate of the difference between the proportions, which is just your sample proportion 1, subtract out your sample proportion 2. In this case, 50 over 250, subtract out 25 over 50. So let me put those in. P1, 50 over 250. Subtract out P hat 2, 25 over 50. Then from the formula, plus or minus. Now, once again, these population proportion confidence intervals, they're based on z-scores rather than t-scores. And we want to figure out the z-score that's associated with the 99% confidence interval. I looked that up on your standard normal distribution, and I came up with 2.575. And then this is multiplied by all this business over here. And that business is, of course, just the standard deviation of the difference of the population proportion. So that standard deviation is equal to sample proportion number 1, again 50 over 250. That multiplied by sample proportion number 1, or 50 over 250 again. All divided by sample size number 1, which is 250. Plus our sample proportion 2, or 25 over 50. Again, multiplied by 1 minus that proportion again, 25 over 50. All divided by sample size number 2, which was 50. Now, of course, when you're calculating out a confidence interval, you have a lower and an upper bound. To calculate out the lower bound, you subtract out this quantity from your point estimate. For the upper bound, you just add it in. For my lower bound, I came up with negative 0.493. And we know that that is, well, we don't know, we're 99% confident that that is less than or equal to the difference between the two population proportions, which is less than or equal to our upper bound, which I came up with negative 0.107. Bam, we got it. So just summing that all up, we can be 99% confident that the true difference between the population proportions, so I meant P1 minus P2, is between negative 0.493 and negative 0.107. Alright, next up I want to check out an example from 10.4 where we're just testing a hypothesis about the difference between population proportions. So I'm going to check out 10.4.57, which is number 5 from your 14th homework assignment. Let me read out the problem statement. I just put up the important information here. Suppose, as part of a national study of economic competitiveness, a marketing research firm randomly sampled 250 adults between ages of 27 and 35 living in City A. So, from City A, sample size number 1 is 250. Next it says, and 170 adults between the ages of 27 and 35 living in City B. So 250 from City A and 170 from City B, so of course sample size number 2 is 170. Then it continues on. Each adult selected in a sample was asked, among other things, whether they had a college degree. From City A, 55 answered yes. So 55 of those 250 had a college degree. And from City B, 73 adults answered yes to they had a college degree. Based on the sample data, can we conclude there is a difference between the population proportions of adults between the ages of 27 and 35 in the two cities with college degrees? Use a level of significance of 0.05 to conduct the appropriate hypothesis test. So once again, what I'm going to do is I'm just going to go through the 5 steps of hypothesis testing that I keep using over and over again. And after I go through those 5 steps, on this one you'll be able to answer all the questions. Alright, so step number 1, determine what you would like to show or prove. Use this to set up your null and alternative hypotheses. And we're asked to see if there is a difference between population proportions. So if there's a difference between the population proportions, of course it makes sense that proportion 1 minus proportion 2 is not going to equal 0, right? So that's how we get our null and alternative hypotheses. Null is that the difference is equal to 0, and of course alternative is what we're trying to show or what we want to prove that they're not equal to 0 or different. Next up, we want to specify a significance level. Again, we were told in the problem statement that the significance level was 0.05. Step number 3, we want to identify our critical z-value. Again, it's a z-value in this situation, not a t-value. And identify a rejection region. Now, because we have an equal to, not equal in the hypotheses, this is going to be a two-tailed test. And a two-tailed test based on the 5% significance level. You look it up in the standard normal distribution, and you should get z-critical values of positive and negative 1.96. So, one critical value here, one critical value there, and of course the rejection areas are anything more extreme than the critical values. Up next now, we want to calculate the z-value of your test statistic. So we got a whole big long formula for that. The z-value of your test statistic is first off the point estimate of the difference between your sample proportions, or sample proportion 1 minus sample proportion 2. We're not given the sample portions directly, we need to calculate those out first. So of course, sample proportion 1 is just going to be the number of people from city A who had a college degree, which was 55, divided by the total number of people surveyed from city A, which was 250. And similarly, sample proportion 2 is going to be 73 over 170. So go ahead and put in those values. 55 over 250. Subtract out sample proportion 2, or 73 over 170. Now, this is subtract out now the hypothesized difference between the two population proportions. Very rarely, never for this class, you might want to hypothesize that the difference between the population proportion might be equal to 10%, less than 10%, something like that. But for this class, we always test hypothesis proportions just to see if there's a difference. And then that means that our hypothesized difference is, of course, just 0. So, hypothesized difference right here is going to be 0. Now divided by this whole mess right here. Now, this is where some people get confused. So here we had p hat 1, or sample proportion 1, p hat 2, or sample proportion 2. But notice down here in the denominator, we just have plain p hat. So what plain p hat is just the overall sample proportion. So it makes sense that the overall sample proportion would be equal to the sum between the two samples that responded that they had a college degree, divided by the overall sum of the two samples, or the overall sum of the sample sizes, or N1 plus N2. Plug in our values, and we would have 55 plus 73 divided by 250 plus 170. So we end up getting an overall sample proportion of 0.30 0.048. Oh, and I guess I put these into decimals too. Sample proportion 1. Of course, you could put it in as 55 over 250, but just how I did it, that came out to 0.22. And sample proportion 2 came out to 0.429. So continue on with plugging those values in. The square root of our overall sample proportion, or 0.3048, multiplied by 1 minus that same proportion, then all multiplied by 1 over sample size 1, or 250, plus 1 over sample size 2, or 1 over 170. You calculate that all out, and you get a z-value of your test statistic equal to negative 4.57. So of course, negative 4.57 is somewhere way over here, clearly in the rejection region. I don't have enough room for step number 5, I just realized, but of course, we're going to reject the null and accept the alternative in this situation. So, in summation, at the 5% significance level, which is equivalent to saying we're 95% confident that the difference between the two proportions is not equal to 0. So if the difference is not equal to 0, we can say that there is a difference then.